I would like to talk a little bit about the origin of magnets. Let's recall what we did last time. Last time, we studied the helium excited state. By that, our idea is that we have one electron in 1s, another electron in 2s. Then we have four possibilities. In the high school level, you may be thinking about up, up, down, 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 up, down. But in the Year 3 quantum mechanics level, you realize that actually these four possibilities have to be written down in a legal or what nature asked us to do. The two electron wave function must be anti-symmetric. And then we have two options. With 1s, 2s, the spatial part can be symmetric. Then it has to go with the spin singlet, the s equals 0 state that is anti-symmetric. Another possibility is that the spatial wave function is symmetric. Then that must go with the s equals 1, the total spin angular momentum equals 1, so-called triplet state. Then an interesting question arises. Which possibility? The singlet go with a symmetric spatial part, or the spin triplet go with an anti-symmetric spatial part? Which one is actually the lower energy excited state? We wrote down the expression to get the energy expectation value, and then we realized there is one difference between the two possibilities. That one difference is a rather interesting term. This is the exchange integral, or the indirect integral. I highlighted here. The two integrals are the same. The only difference is the sign before it. You see a plus, you see a minus. The other terms are the same. Therefore, we realize one thing. In order to distinguish which possibility has the lower energy, it is determined by the sign of this very peculiar integral that only happens because we have quantum mechanics. First of all, this integral, the general form is this, does not carry any classical physics interpretation. By that we mean, we cannot find anything with the single electron wave function square. If we see that, we can interpret that term as a probability density according to Max Born's interpretation of the wave function. However, we don't see it here. It is entirely a quantum consequence. But that determines whether spin singlet or spin triplet is the lower energy excited state for helium atom. In helium, it turns out the triplet state is the lower energy one, but there is no one size fits all here. Each atom, you have to do a separate integral of this kind in order to determine the sign of this term. And then we see a very interesting phenomenon. In helium excited state, after doing the calculation, we found that this spin triplet state is of slightly lower energy. If we look into the S equal 1 state, up, up, down, down, and up, down, plus down, up, we have this vector model thing already shown, then basically the two spins tend to align with each other in S equals 1, and they tend to cancel each other in this S equals 0 singlet state. And that is the first hint in the history of mankind that magnetism, or the origin of magnetism, actually comes from this kind of exchange Coulomb integral. If you look into the helium atom closer, you see that it has nothing to do with the spin magnetic dipole moment interaction. No. In the integral, what is in between is Coulombic. So this is another breakthrough in the understanding of mankind in magnetism. It is Coulombic origin. And due to the antisymmetric requirement of wave functions, many electron wave function in a solid that is magnetic, we have this kind of very strange integral. So it is at this point, I think 1927 or so, 28, that we start to understand the origin of magnetism. Okay, so this is the beginning of these few pages. So we have a few elemental magnetic materials, not many. The whole periodic table, you have 90 something, only a few, but they are very useful. Okay, so the famous ones are iron, cobalt, nickel, and then they have a few d electrons in the 3d row. Okay, something like 4 electrons, 5 electrons, 6 electrons. And according to what we mentioned last time near the end, there is something called the Hund's rule telling us how to fill in the d state. For example, you have 4 electrons in the d level, then we better put it as up, 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 instead of pairing it up, down, up, down. It turns out that after many calculations, up, 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 up will have the lower energy than pair it up, up, down, up, down. And because you have up, 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 up in the d state, the net spin angular momentum of that atom, these magnetic atoms, will be big. So first of all, the origin is highly quantum in several ways. The first, it has to do with spin alignment. And spin is already very quantum stuff. There's no classical analogy. Secondly, we now understand it is due to Coulombic interaction rather than classical dipole moment interaction. Then we have this kind of model Hamiltonian that is very famous in condensed matter physics. Thousands of PhD or master theses have been written around this topic. So basically, after we understand it is spin alignment, if they tend to align, this is ferromagnet. If not, then it is an anti-ferromagnet. Then we can write down a model Hamiltonian, meaning we construct a model such as to capture the alignment of spins as the origin of magnetism. And here it is. If we consider only 2 spins, then we know what to do. Aligned with one energy that is lower, anti-aligned with another energy that is slightly higher. Okay? And then it is easy to construct such a model of 2 spins. For example, this will work. The minus sign just to make sure that if this is aligned, then this is very minus happy, lower energy, okay? And then if this is anti-aligned, that will have a minus sign itself, that will make this positive, higher energy, not so happy, okay? So now, if we do this, and then if we follow previously, how we can treat S1 dot S2, we have the square, total square, things like that, that already have our model in mind, because according to singlet and triplet, there will be a splitting. We did that in spin orbit interaction. We did that in the hyperfine structure, the same physics. Here, we construct it as a model for magnetism. Well, in a solid, magnetic solid, we don't only have two magnetic atoms. We have many. So we have an array. Then a standard model of magnetism is this form. So we have Si dot Sj pretending to be modeling alignment happy, anti-alignment not happy. And then we have to sum over many neighbors, you see? Okay, I'm highlighting some neighbors. So we have to sum over all this. And usually, it is sufficient, and rather strangely, it is sufficient to include nearest neighbor interactions. By that we mean, we just want this spin I to influence its four nearest neighbors. With such kind of minus k, k is an energy, if aligned, there will be lower energy proportional to k. So if we only include nearest neighbors, that means one spin here only wants to persuade its four neighbors to go in the direction of this spin. So I'm just persuading my four nearest neighbor, I'm up, you better go with me, up, the energy will be lower. Okay, now that is another very profound concept in the development of physics. We only need short range interaction, meaning a spin just wants to influence locally its neighbors. If I'm up, you go with me, up, 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 please, okay? Because the energy is lower. But that will be sufficient if the condition is right, meaning lower temperature, to lead to a long-range ordering. That is to say, in the whole sample, the spin tend to be aligned in the same direction. Now, that is something highly non-trivial. Only local interaction could lead to global ordering. Okay? In statistical mechanics, in the topic of phase transitions, you will have the chance to see more of this. But this is the beginning of a big, big subject. Just a page to bring out the physics of magnetism or magnetic phase transitions. I think from primary school, you know something about that. You take a piece of magnet, you bring it close to a fire or heat it up, okay? Then, as the temperature goes up, the magnet will lose its magnetic properties. It becomes non-magnetic. So temperature is an effect, right? So basically, low temperature, you will see ferromagnetic behavior. High temperature, you see non-magnetic behavior, okay? And that is what we mean by phase transition. We have a ferromagnetic phase, we have a metal phase, ordinary conductor phase. So what happens in terms of thermodynamics or what you are learning in statistical physics? So here is a very brief one-page idea. Let's think about zero temperature. Then it's simple. We just look at the Hamiltonian, the model Hamiltonian. If all the spins are aligned, the dot product will be very big. With a minus sign in front, the energy will be the lowest. That is what zero temperature means. Zero temperature, look for the lowest energy state. So zero temperature, all the spin will be ordered despite the interaction, the inference is nearest neighbor only. Okay, so no temperature, very low temperature with ferromagnetic behavior, not surprising. Now, with higher temperature, what happened then? Then you have to go into your thermal physics, okay? Your thermal physics will tell you that the quantity to be minimized is not the internal energy only. For equilibrium, it is the so-called Helmholtz free energy. I use F here, some books use A. Okay, it doesn't matter, it is that U minus Ts. Now, in addition to looking for a lower configuration of the spin for U, the entropy effect kicks in. And the entropy goes with the temperature and with a minus sign in front. That is to say, if the entropy takes on a higher value, it may help because minus Ts will be negative and you're trying to minimize F, looking for a lower F, okay? So summarizing, that is the common sense phrase, temperature tends to randomize the system, okay? Behind it is that by randomizing it, S increases, this minus Ts term increases, so it may help to minimize F, okay? Now, how to think about this entropy term? Start with an order thing. If you just pick one spin and flip it, that will be a disorder out of the original ordered situation. Okay? Now, you count how many ways you can flip one spin out of n. You can pick any one to do, so you have n ways. I think in your statistical physics course, you may start at this point counting microstates. Have you got to that point? Those in Professor Gore's, okay? Now you have n, you're counting w, all right? So K log w is the entropy. Now you can imagine, if not flipping one, but how about two spins? Then you have to count, right? C, N, 2, then you have this kind of numbers. And then you have K log W, and then you have to play with F to minimize F. So therefore, it is easy to think about that as temperature increases, the original zero temperature configuration will be randomized. As temperature increases, it will be randomized to an extent that when you if you look at what is the net magnetism, you will have equal chance to find a spin to be up and down. Then the net will be zero, the magnetic alignment will be lost. Okay, so that is the physics behind this phase transitions from low temperature to high temperature, this ferromagnetic to non-magnetic transition. Okay, you will see more in your statistical mechanics or statistical physics course, but this is basically the idea. The rest is to work it out mathematically. So I will end this discussion on magnetism here. Then the very last part of this module is just to take another look at the periodic table. You have seen this many times from high school, maybe year 1 chemistry course. I hope this time around you will have a better appreciation and a better sense. When you see this, you should appreciate there is a lot of hard work behind it. Any atom beyond hydrogen is highly complicated, simply because you have 2 electron problems, 3 electron problems, 92 electron problems. It's hopeless. Nonetheless, physicists can make such big progress and establish the periodic table and understand what is happening. We have done a lot of approximations, but it turns out nature is kind to us. Those approximations works very well. Let's recap what we did. We tried to reduce many electron problems to single electron atomic orbital problems. That has to do with a lot of self-consistent calculation, Hartree-Fock way to handle electron-electron interaction. I think nowadays, even more high-tech method has been established under something called the density functional theory. Again, that won the Nobel Prize of Chemistry in the 1990s. It all stemmed from our discussion of Hartree-Fock self-consistent method. And now, after establishing atomic orbitals, we rescue the picture based on hydrogen. We regained the idea of 1s, 2s, 2p, things like that. The second question is how to fill in the electrons. Now we realize the higher level understanding is the antisymmetric property of the many electron wave function. A byproduct of that, when we invoked single electron atomic orbitals, is the Pauli exclusion principle. Together, these two parts, as we discussed throughout the various parts, give us the understanding of atoms and the periodic table. The ground state of an atom becomes, we fill in the atomic orbitals according to the Pauli exclusion principle. And then we have this idea of the periodic table. This was the 1869 version, kind of the original version of the periodic table. 2 years ago, the United Nations declared 2019 was the International Year of the Periodic Table. I look up the latest version. It is the latest version on this page. It was released 2018, December the 1st. And up to now, it has not been further updated. You see, it is now up to 118. Named it, okay? Here. And there are always a few waiting to be named. And those will not appear in the formal announced or most latest updated periodic table. For those waiting to be named, there are criteria. For example, further experiments must be done to confirm the announced result. So the elements at this point carry no name. Only when there are sufficient experimental evidence, then this place, called the International Union of Pure and Applied Chemistry, IUPAC, they will meet every few years and then will give the right of naming a new element to the lab that is first discover it. Okay, so near the end of the named element, you will find something rather funny. It's too small. So you find Moscoulium, so it must be discovered by a lab in Moscow. Livermorium, so it is discovered in the Livermore lab near Berkeley. Tennesseeium, so somewhere in Tennessee there's a lab. Okay, so near the there is an Einsteinium. It's too small. That is one after Einstein, isn't it? Can't find it. Okay, so but key point, what you can find on Earth stable is up to 92. Here. Okay, so uranium is the last element that we can find on Earth that is stable. From 93 onwards, they can be put together in a lab situation, and then they will decay. So they are short life elements. Here, the 98, sorry. 98. 99, this is Einsteinium, okay? This is after Einstein for some reason. Okay, so this is the latest periodic table. The story behind it is wonderful. If you have time, look it up. Periodic. So it will be good to look at some periodic properties. Here I show you several. The most noticeable is the ionization energy. What is it? It is actually called the first ionization energy, meaning you take a neutral atom and you look for the energy that is required to take out the least bounded electron. Okay? For example, in an atom, if you take out the 1s1, you have to provide more energy than one of the outer most electrons. So this is the first ionization energy in electron volt. It is very apparent that you see some periodic structure. Okay, in particular, helium is very stable, therefore you need to put in a lot of energies. There's a peak here in order to take out one electron from the helium ground state. And similar for the so-called inert gases. Okay, and then you don't need much energy to take out an electron from sodium, potassium, the group 1 elements. And that makes this sodium is a so-called exemplary metal. If you learn solid state physics, sodium is usually the example of a well-behaving metal. Although practically it is not a good metal to make things for practical use, but periodically is a very good metal because this outermost electron can be easily detached and wandering around, so to make this sodium a good metal. I also give you the other thing called electron affinity. Okay, it is also needed. This is the opposite of ionization. It is related to the following. If I take an atom, I add one electron into it. Okay, what is the change in energy? Basically, it is like that. Okay, now, for example, fluorine. Fluorine is here. Okay, so it is 2p5. From high school chemistry, you have remembered that, well, give it one more, it is happy. Okay, what does it mean? First of all, quantum mechanically, you need to do two calculations. Fluorine neutral atom, you have to do the hydrogen, a lot of things. Then you look at the ground state. Then you have a new Hamiltonian called F minus, fluorine ion. Because you have 6 electrons, the Hamiltonian term will be different in the p, 6 electron in the p states. So you have a different Hamiltonian. You have to redo the calculation again and look for F minus ground state. Therefore, you have neutral fluorine atom ground state energy. You have F minus ion ground state energy. You see which one, how different they are, then you get the electron affinity. Okay? So, with this understanding, many years of hard work, at the end, you have this rather familiar so-called electron configuration. This is a way to express how you fill in the electrons into the atomic orbitals. For example, helium, we will say it is 1s superscript 2. So we put 2 electrons in the 1s state. Fluorine, for example, actually it is 1s2. So that's why there's a helium bracket here. They don't want to write so many things. So this refers to 1s2. And then 2s2, 2p5. Okay, now you need it to understand molecules, and we will do molecular physics later. Similarly, you go down the row, you see this kind of periodic filling of the s orbital, p orbital, and so on. Okay, so this is the electronic configuration of atoms in ground state. And that has a lot of physics in it. For example, fluorine, could it form a bond with hydrogen fluoride? So you have 1 electron here lonely, waiting to pair up to form a bond. Giving it to this P5 may be good. It will lower the energy. If they come together, do something, the energy is lower than individual atoms, then nature will do it. So you have compounds, then you have molecules, then you have solids, then you have ourselves. Okay, you have yourself. Okay, so we are composed of many molecules. So the table here, I just show you the whole periodic table. This one is up to 104. Okay, now just to go through a few standard features, then we will end this module. We discuss hydrogen, helium. How about lithium? So lithium, we fill 1s, completely filled, and then the 2s. I draw it up here, it could be down, it doesn't matter. Okay, and now you can think, if you are going to do that quantum mechanically, you really need to write down a 3x3 determinant, the selected determinant, and set up some calculations self-consistently in order to really calculate the atomic orbitals. And that is the result, and then we fill electrons in. as a picture. That is the story behind all this simple way of writing things down. Okay, and now obviously these two pair up in 1s is in the inner, so-called inner shell, and then this lonely electron is quite ready to form bonds with other things. So it will be chemically rather active. Since it is a lonely electron out there, you don't need much energy to take it out. That is the first ionization energy. You look at the table, it's about 5 GeV. We introduced the term symbol previously in hydrogen context. You can do it the same here, okay? You have an S state, L equals 0, so the whole thing is L equals 0, the S in the middle. You only have one electron, so you only have spin, okay? And L is 0, the total must be half, right? L plus half. This is the only choice. You don't have L minus half because it cannot be negative. Therefore, J is half in the lower corner, okay? And spin, 2s plus 1, okay? This can be up or down. That is to say, you have this freedom. And this is the 2s plus 1, which is 2. Beryllium. The ground state is actually all filled, 1s2, 2s2. Then you may think that beryllium should not be chemically very active, but in fact, it can form something. For example, it can form some very funny thing called BeH2 with 2 hydrogen, and it is a linear molecule. Now, that is something highly non-trivial, right? How come? That is a topic we will pick up in the physics of molecules later. Basically, the idea is that maybe if we think in terms of an electron being instantaneously or temporarily promoted to a nearby excited state 2p, then there are 2 electrons that could form a bond with 2 atoms. And when they form bonds, usually energy will be lowered. Perhaps that lower in energy is sufficient to counteract this increase in energy in promoting from 2s to 2p. So net energy gained. And that is the story. But the story is more complicated than that because that has to do with something called hybridization. In this particular case, it's the simplest thing called sp hybridization. You may have heard sp3 hybridization in some funny 109-degree bonding stuff. And that is the more complicated version of this beryllium dihydride, BeH2. And then we start filling the 2p from boron to neon. So we just keep on filling this 2p1 and then 2p2 and so on. So you have boron up to fluorine, you have 2p5. I already mentioned fluorine ion is a very common ion we encounter in molecular context. It has 1 more electron. So basically, you need to do one calculation for neutral fluorine atom, a separate calculation for fluorine ion. You compare ground state energy. The result is that it happens. This has a lower ground state energy than that. So overall, if you give F neutral atom 1 more electron, there is an energy difference that is called electron affinity. So there are complications that you must appreciate. in more advanced atomic physics courses, you will encounter such a question. For example, carbon. I have 2 electrons in the 2p state. But I know that for p orbitals at px, py, pz, up, down spin, there are 6 together. I have 2 electrons. What to do? Okay, should I put it here, put it there? Okay, or put it here, put it there? What should I do? Okay, up, down first, or up, up? Does it matter? Okay, so if you think about the question, actually is rather complicated because you can count how many ways you can put 2 electrons into 6 states. There are 15 ways, and therefore you may want to try all different ways and then find the lowest energy. People did that. And that is summarized in something called the Hund's rule. So you will learn the Hund's rule in a atomic physics course. How about the other elements beyond the first up to 2s? Then you start filling 3s1, 3s2, and so on. And that is sodium onwards. Okay, so it is similar to the things that we just discussed. And that's why we have the periodic table. It is good to take a last look at some feature of the wave function before we leave the topic of atoms. We did this page in molecular physics. It is a broad picture, of course, not very accurate. It's not accurate because every atom is a separate quantum mechanics problem. We don't have one size fit all atomic wave functions. Okay, nonetheless, it is good to say take hydrogen or take something as a ballpark. Well, at least the big picture is right. So here, it's not the wave function, it is the radial probability. Okay, what does it mean? It is R squared times the radial wave functions squared. Okay, so it is the radial probability density. So I would like you to look, for example, the 4s and the 3d. You see, the 4s is more extended, although 4s has a slightly lower energy atomic orbital than 3d. But the 4s are more extended, and the 3d, relatively speaking, is closer to the origin, the nucleus. So it is kind of more inner than 4s. And that explains the physics of transition metals. The transition metals are those filling the 3d, and this is the row. In the middle of a few very important things, magnetic materials, okay? Chemically, it was found that they behave rather similarly, okay? That is to say, in terms of chemical reaction, even they are, in the periodic table, they are quite far away, so-called, okay? But they behave very similarly. The reason is that the 4s is filled, and then they start filling in the 3d2, 3d3, and so on, okay? And now, when you add electrons into the 3d, the electrons go into a kind of a inner orbital. The chemistry is controlled by the farther 4s state, because the farther wave function is the first one that can feel a second atom coming in. And if their wave functions start to feel each other, to overlap, in the middle part of between the two atoms, then they can think about, hey, can we do something to form a bond so as together the energy will be lowered? If yes, then there will be a bond formed with the other atom. So it is the outer orbital that matters in chemistry. And then we have, I just mentioned the Hund's rule here. After many calculations, Hund's rule summarizes the quantum mechanical results. For example, if you have 5 electrons to fill in D, what to do? Don't do it as up, down, up, okay? Do it as up, 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 up. That will have the lowest energy arrangement. So that is Hund's rule number 1. Hund's rule is very funny. There are 3 rules, but there is an order to exercise the 3 rules, meaning the number 1 rule is the strongest, second rule is medium, the last rule is weakest, meaning sometimes the Hund's rule number 3 is not obeyed. But Hund's rule number 1 always works. And then after the transition elements, we will encounter a lot of very useful things, gallium, germanium, arsenide, what is this, selenium. So they are useful in semiconductor industry. Germanium, on top of it is silicon. So this two is the most important elemental semiconductor. Many money has been generated. The most useful material on Earth, sand, basically. You take sand and then remove the oxygen, you get very good silicon. And then gallium arsenide, indium phosphide. So this one compound, this is group 3, this is group 5, and they can only be made in the lab. You don't have a mind to dig it out, but they are very useful semiconductor due to their special band structure. Similarly, from some group 2 and group 6 elements, you have other compounds that are semiconductors very useful. For example, these two can be put together to make the night vision equipments. So last page before we end this module, the big picture is that we need quantum mechanics to understand atoms. There has been much work to reduce the many electron problem to single electron atomic orbital problem. And that was successful, and we have this idea of atomic orbitals. Then we discussed the antisymmetric requirement of many electron wave functions, and the byproduct is your old friend Pauli exclusion principle. By putting these two big quantum ideas together, we have the periodic table and understanding of the physics of all the atoms. And only from that point, we can possibly understand bonding between atoms or among atoms to form a bigger molecules. This is a topic that we will pick up after we do light and atom interaction. So this formally ends this module, okay? So let's take a break now, and then we will start the next part of the course.